China has just released a new set of images of 3I Atlas, and they reveal details that never appeared in NASA's most recent public update. In these frames, the object looks noticeably brighter, with a thicker coma, a wider dust cloud, and a sudden surge in light that simply wasn't present in NASA's earlier data. This ancient interstellar traveler, estimated to be billions of years old, made its closest pass by Mars on October 3rd. During that brief window, Chinese scientists managed to capture several striking snapshots that show the object in a dramatically different state. What makes this especially intriguing is the timing. These changes occurred during hours when NASA reported no new observations at all. That gap raises uncomfortable questions. What exactly happened during that period, and why did the object appear so altered by the time China imaged it? China's new images suggest we're not looking at the same calm, predictable body NASA had presented just hours before. The coma in the Chinese data looks transformed, far more active, far less stable, and nothing like what had been previously shown. Now we're seeing fresh images of 3I Atlas, only the third interstellar object ever observed from Earth, and it's already challenging what we thought we understood. The difference was obvious right away. As soon as the new frames were analyzed, the object's changed appearance became impossible to miss. The first images showed a sudden increase in brightness spreading across the entire coma. That coma, the cloud of gas and dust surrounding the icy core, had expanded to nearly 400,000 kilometers wide. That's about 3 times the diameter of Earth and far larger than anything NASA recorded before the observation gap. This marked the first time scientists had ever seen a glow forming ahead of the object, pointing toward the sun. The edges of the cloud were sharper than expected, and internal light levels rose within a very short window, something that never appeared in any Western dataset. The next major change showed up in the tail. NASA's final release before the gap showed the tail extending straight and cleanly away from the sun, stable and unchanged. But in the new images, the tail showed a subtle bend toward the sun. That bend indicates the flow of dust shifted during the blackout period. This kind of shift usually happens when fresh jets suddenly open on the surface, and it confirms the object released material in a direction that hadn't been seen in NASA's earlier images. From these images alone, it's clear the object is active, strong evidence that it is indeed a comet. The dust distribution inside the coma also looked very different. The brightness pattern suggested larger dust grains were mixed into the cloud, something that was missing from NASA's pre-gap data. Larger grains typically form when deeper layers begin breaking apart as heat increases. The uneven layered structure seen in the coma supports this, especially since NASA's earlier observations showed a thinner, smoother dust cloud. To visualize it simply, the sun is here, the comet is here, and the solar wind flows past it, pushing material behind the object like a sail. But something changed in how that material was released. Spectroscopic analysis revealed another critical detail. The new images showed a much stronger carbon dioxide signal than what NASA detected before the gap. A spike like this points to deeper ice warming up and escaping into space. This kind of release can happen very quickly when sunlight reaches a section of the surface that had previously been shielded. All of these changes occurred within a short window that only one country managed to capture. The expanded and altered coma, the bent tail, the presence of larger dust grains, and the stronger carbon dioxide signature all belong to a phase of activity that NASA never recorded. Data from the Webb telescope shows that the surrounding plume is made up mostly of carbon dioxide, about 95% by mass. That's why these new images matter. They capture the exact moment when the object responded to sunlight in a way that never appeared in Western observations. More importantly, they reveal the first clear signs of rapid and dramatic behavioral change in 3I Atlas. This is a major update, possibly the biggest one yet, on our favorite interstellar visitor, and it may turn out to be one of the most significant discoveries in the entire solar system. What NASA released before the observation blackout, NASA published several images of 3I Atlas. Those frames showed a calm, stable object with a thin coma, a straight tail, and no sudden increase in brightness. Nothing in that data suggested the object was about to become more active. What made the comet especially interesting even then was its unusual structure. It clearly had a traditional tail being pushed away by the sun's radiation, but it also appeared to show a forward-facing component. Even so, the images gave no indication that a major change was underway. After that update, the flow of new data stopped. The observation gap that followed is the exact window China continued to monitor in full. In NASA's public archive, there are no raw images from the object's perihelion passage. Perihelion is the point in a comet's orbit when it comes closest to the sun. This is when solar radiation heats the surface most intensely, vaporizing ice and driving out gas and dust. Because of that, perihelion is the most active and most valuable time to observe a comet. Any material released during this phase can be quickly destroyed by sunlight before it has a chance to fully evolve or become visible later. During those critical hours, NASA did not publish brightness curves, new dust measurements, or updated information on the tail's structure. When observations resumed, the object had already moved away from its most active region. As a result, the changes captured later in China's images do not appear anywhere in NASA's public record. This gap also limits what scientists can determine about the object's nucleus. Its exact size is difficult to pin down, partly because of the object's small scale, but also because increased activity can hide the solid core beneath expanding gas and dust. NASA explained the absence of data as routine instrument downtime for calibration, which is standard practice at major observatories. The issue is timing. That maintenance window happened to coincide with perihelion, the moment when continuous observation is most important for understanding how an object responds to solar heating. NASA also has not directly addressed the clear differences between its final image set and the newer data released by China. NASA's images showed a thin coma, while China observed a larger and brighter one. NASA recorded a straight tail, while China documented a slight bend. NASA detected only a weak carbon dioxide signal, while China measured a much stronger one. These discrepancies remain unresolved because NASA has not released comparable observations from the same time period. They have not challenged China's measurements, nor have they published alternate frames showing similar levels of activity. China captured the hours missing from NASA's sequence, and those hours contain the changes that reshaped how the object appeared in later images. Because of this, scientists now have a clearer picture of the object's path through space, and that raises a new possibility. This may not just be another interstellar visitor, but a newly identified, previously unknown object, one that could potentially pose a future hazard. Until NASA releases data from that same missing window, the two records will continue to show different sides of the same event. Those missing frames are critical because perihelion is the one moment in a comet's orbit when its internal structure becomes visible. As sunlight penetrates deeper layers, different types of ice vaporize at different temperatures, and each one leaves behind a distinct chemical signature. Without continuous observations during this phase, scientists lose the ability to track how surface layers peel away and how the comet's chemistry evolves over time. China's images captured that process as it began, while NASA's observation sequence ended just before the reaction started. Another key factor is the timing of the dust release. The size and speed of the particles being thrown off help researchers determine how tightly the surface material is bound together. That in turn offers clues about whether the comet originally formed in a colder or warmer region of its home star system. China's data recorded the very start of this release, providing a crucial reference point that shows how the surface responded as temperatures rose. NASA's data, which stops before the active phase, cannot provide that baseline. When both data sets are placed in order, the transformation becomes obvious. The comet NASA observed before perihelion and the comet China observed during perihelion are the same object, but seen at two very different stages of solar heating. This behavior is normal for icy bodies that pass close to the sun. The outer layers often remain quiet until sunlight reaches deeper ice, and once that ice begins to warm, the entire surface can change within hours. NASA captured the quiet stage. China recorded the moment the surface began to react. The first major change appeared in the coma. NASA's final images showed a thin halo that gradually faded at the edges. China, however, recorded a much wider halo with sharp boundaries and stronger brightness across the entire cloud. That expansion signals a sudden release of gas and dust from the surface. something NASA did not observe. Near perihelion, heat can travel through cracks and pores in the ice, reaching buried pockets below. When those pockets warm up, the ice can rupture outward, carrying material that forms a brighter and denser coma. The structure of the tail also shifted during this period. NASA documented a straight tail extending cleanly away from the sun. China captured a slight bend toward the sun, indicating that dust was being expelled in a new direction. This kind of shift can happen when a surface jet opens at a different angle than before. Even a small jet can noticeably alter the tail's shape because the dust particles are lightweight and travel long distances once they leave the surface. The result is a dense, massive cloud of gas and dust that is then pushed away by solar radiation. All of these changes match activity seen in many other comets as they approach perihelion. The most dramatic difference appears in the brightness measurements. NASA recorded a slow, steady increase in light. China measured a sudden spike that occurred over a very short time span. A rapid rise like this often happens when deeper ice fractures and releases gas in a single burst. Because NASA's data ends before that moment, the sharp increase appears only in China's brightness curve. And this type of sudden brightening is well documented in comet science. In the case of 3I Atlas, the object appears as a fuzzy ball of light. That may seem simple, but this behavior fits well within known comet science. A famous example is Comet 17P/Holmes, which suddenly brightened by a factor of nearly 500,000 over just 42 hours in October 2007, when buried ice vaporized all at once. The change seen in 3I Atlas is far smaller, but the pattern is very similar. Comets often show their strongest reactions during their closest approach to the sun, and those reactions can unfold rapidly. Dust composition adds another important layer to this story. NASA's data showed mostly fine dust particles, which typically come from the very outer surface of a comet. China's observations, however, detected larger grains spread throughout the coma. That difference matters. Larger grains usually form when stronger, deeper layers break apart beneath the surface. These heavier particles don't travel far unless a fresh jet opens up. Their presence confirms that solar heating reached deeper levels of the comet during the hours NASA did not observe. China's measurements also helped refine the comet's trajectory, something that can't be fully explained by imaging alone. Additional data collected during the active phase reduced positional uncertainty by about 30%. When a comet's coma expands and jets activate, tiny forces push on the nucleus and can slightly alter its path. By capturing the moment when those forces were strongest, China gathered information NASA simply didn't have. None of this suggests a contradiction between the two data sets. Instead, they show the same comet at two different moments in time. NASA observed 3I Atlas during its stable phase before perihelion. China observed it during its most active phase, right at closest approach to the sun. The differences come down to timing, and the missing hours contain the reactions that explain why the comet looks so different in each record. So what does this mean for 3I Atlas today? The perihelion observations reveal that it reacted far more strongly to solar heating than early data suggested. Before perihelion, the comet appeared calm and predictable. During perihelion, it behaved like an object under sudden stress. That short window reshaped the coma, bent the tail, and caused a brightness increase that NASA never recorded. What once seemed like a quiet visitor suddenly became a far more dynamic object. Interstellar objects themselves are a new frontier. We've only begun detecting them over the past decade, and we don't know whether similar visitors passed through our solar system before we had the tools to notice them. The wider and brighter coma seen in China's images is the clearest sign of this transformation. A coma forms when ice turns into widening and carries dust away from the surface. In the pre-perihelion images, that cloud remained small and faint. During the active phase, it expanded dramatically. Growth on that scale means deeper ice layers began to vaporize. The surface didn't just warm, it opened up and released stored material. Changes in dust grain size reinforce this conclusion. NASA's data showed mostly fine dust, which usually comes from loose material on the outer crust. China detected larger grains mixed throughout the coma. These heavier particles are harder to lift, meaning deeper and more tightly bound material broke free. This points to a layered nucleus, with older compact ice beneath a softer outer shell. The tail shift adds another clue about how this activity unfolded. Comet tails form when sunlight and the solar wind drag dust away from the sun. NASA recorded a straight tail that followed this expected direction. China observed a slight bend toward the sun, indicating that material was being released at a new angle, likely from a freshly opened jet. Claims suggesting alien technology do not appear in the scientific interpretation. What the data shows instead is a natural interstellar object responding rapidly and dramatically to intense solar heating, exactly the kind of behavior scientists expect when a comet reaches perihelion. The slight bend in 3I Atlas's tail suggests that a jet on the comet's surface pushed dust away from the mainstream. Even a relatively small jet can tilt the tail if it operates long enough, and the angle captured in the images helps pinpoint where the jet may have formed. Brightness measurements showed that this was not a slow, gradual change. NASA recorded a steady increase in light as the comet approached the sun. China, however, observed a sharp spike in brightness within a narrow window of time. This pattern matches what scientists call a sudden venting event. A sealed pocket of ice fractures, gas rushes out, and the coma brightens almost instantly. After this initial burst, the brightness gradually returns to a slower rise. Because NASA's sequence ended before this spike occurred, it appears only in China's data. The stronger carbon dioxide signal in China's spectra completes the picture. Carbon dioxide ice is more volatile than water ice when close to the sun, but it often lies deeper beneath the surface. When sunlight finally reaches these buried layers, the gas escapes and leaves a distinct chemical signature. NASA's weaker signal implies that these layers remain sealed during their observation window. China's stronger signal shows that the deeper ice were finally exposed during the hours NASA missed. China's updated orbit calculations also reflect the mechanical effect of these jets. When gas flows in a specific direction, it applies a small force to the nucleus, a non-gravitational push that can subtly alter the comet's trajectory over time. Additional measurements taken during this active phase reduced uncertainty in the comet's future position by about 30%. These observations confirm that the burst did not make 3I Atlas a threat, while also showing that its path is not purely passive. For comet researchers, these perihelion observations provide a rare opportunity to study an object from beyond our solar system. 3I Atlas entered from interstellar space and will leave again, never to return. Every detail, changes in brightness, tail shape, dust composition, and chemical signals, offers insight into the environment where it formed. The stronger carbon dioxide signature suggests a cold birthplace rich in volatile ices. The heavier dust grains indicate a long history of compaction inside the nucleus. And the sudden perihelion outburst demonstrates that these layers, stable for millions of years, can still react violently when exposed to heat. This event also underscores the importance of complete observational coverage. Had astronomers relied solely on NASA's data, 3I Atlas would have appeared as a calm, uneventful comet. With China's perihelion images, the same object becomes a textbook example of rapid activation. This highlights how future interstellar visitors should be monitored. Dense observation windows are crucial around perihelion, and maintenance or downtime should be minimized when rare objects reach peak heating. Currently, 3I Atlas is moving away from the sun and gradually cooling. Its coma will shrink as gas production drops, and its tail will thin and straighten. Follow-up observations are planned with ground-based telescopes in both hemispheres. Scientists aim to track how quickly the coma contracts, how long any jets continue to operate, and whether the chemical composition returns to its pre-perihelion state. Eventually, all stages will be combined into a single, continuous record. The calm approach captured by NASA, the sudden outburst seen by China, and the fading tail that follows. This complete timeline shows how an interstellar object reacts to a star it did not originate from. In that sense, 3I Atlas is more than just a comet. It is a sample of another star system's building blocks. And the perihelion images reveal that these building blocks are far more reactive than they first appeared. Why this matters if 3I Atlas were artificial, we might expect it to maneuver, send signals, or display lights. But the real significance of China's new images lies in how they complete the observational record of the comet. NASA's data ends before the object became active, while China's begins right in the middle of that active phase. When both sequences are viewed in order, the previously missing hours become the turning point that explains why the comet appeared so different in each dataset. These new frames reveal changes that were invisible in any Western release. The rapid expansion of the coma, the slight bend in the tail, the stronger carbon dioxide signal, and the sharp spike in brightness, all of which occurred during the period that only China observed. Together, these features document how the comet's surface reacted as sunlight penetrated deeper layers, capturing the precise moment it shifted from a quiet state to an active one. China's measurements also refine the comet's trajectory. Extra data points collected during this period of intense solar heating reduced uncertainty in its path, providing a clearer prediction for how it will move as it leaves the inner solar system. This confirms that the activity seen in the new images is real, not an error or artifact. The importance of these observations is straightforward. NASA captured the comet before it responded to sunlight. China captured it during that response. Both datasets describe the same object at different stages, and the new images fill the gap that explains its change in appearance. These observations are entirely consistent with natural comet behavior. They show how an interstellar object reacts when sunlight reaches fresh layers of ice and dust. This is particularly valuable because interstellar comets carry chemical material from other star systems. Each measurement gives astronomers clues about how different systems form and evolve. As 3I Atlas moves farther from the sun, its surface will settle back down. The brief surge of activity will remain preserved only in the frames recorded during the previously missing window. Those images capture the single moment when the comet revealed its most active state. And that is why this new release is so significant. It completes the record and provides the missing context needed to fully understand how the comet behaved at the height of solar heating.